Hey everyone, this is Hossein, and in this episode we'll continue reviewing the article Magnesium Additive Manufacturing. I hope it will be useful. Now for those of you following along with the article PDF as we've seen in the previous episode, we're moving on to page 3. Let's take a moment to look at figure 1 together. As we can see in this figure, schematic of A. Powder bed fusion, B. Wire arc additive manufacturing, C. Paste extrusion deposition, D. Friction stir additive manufacturing, and E. Jetting technologies. All of them are different types of additive manufacturing technologies. All of these approaches can be used to produce magnesium-based scaffold. Now let's move on to figure 2. Please picture a series of tiny porous cubes, like this figure, which is created from a process called laser powder bed fusion, made from magnesium alloy, WE43 magnesium alloy, which one created with a process called laser powder bed fusion, or LPBF. The idea is to use these complex laser structures as bond scaffolds because magnesium alloys can dissolve safely in the human body while helping new tissue grow. Here the focus is on how they hold up when it comes to mechanical strength, how they corrode, and how biocompatible they are. Thanks to carefully managed risk controls during laser-based additive manufacturing, researchers can now reliably produce magnesium implants in a variety of compositions. LPBF itself is recognized as a powerful technique, offering a high level of accuracy and reproducibility, along with superior metallurgical and mechanical properties. Among the different Mg alloys currently studied, you'll often see pure Mg, MgAl, MgRe or rare earth, and MgZn or zirconia. But you can see in this figure WE43 magnesium alloy. It is a high strength magnesium alloy. They're fabricated in 3 different sizes by Dr. Bathai. Picture the adult human skeleton. By the time we're fully grown, we typically have between 206 and 213 bones forming a dynamic support structure. These bones don't just keep us upright, they also allow for movement, facilitate respiration, and protect vital organs. On top of that, they store important minerals like magnesium, calcium, and phosphorus, and even produce white blood cells and red blood cells, and also platelets in their bone marrows. As we age, our bones undergo continual reshaping, a natural process known as biological remodeling. When you zoom in closer, you'll see that bone has a hierarchical structure from the macro level to the micro and nanoscale, just like what's shown in figure 3. In terms of classifications, bones come in 2 main types, trabecular and cortical. Trabecular bone usually features a higher porosity, somewhere between 50% and 90%, while cortical bone is denser, with a porosity around 30% to 5%. So smaller, though these values can shift based on a person's age and bone's location in the body. And as you can see, figure 3 excellently demonstrates these various types of bones. And as the article continues, bone regeneration at a damaged site hinged on an implant's ability to restore the bone's physical function. That's obvious. But ideally, these implants need to mimic native bone as closely as possible. That means 3 key factors come into play. Matching mechanical properties so they can handle loads without causing stress shielding, offering high biocompatibility to promote cell adhesion and not releasing any harmful ions, and having a porous structure. What makes magnesium and its alloys so appealing in this context? They naturally degrade in the body and they're biocompatible, In fact, many magnesium materials possess mechanical strength and very similar to human body, to human bones. So, as we understand, this similarity in strength, along with biocompatibility, covers two essential requirements for implant design. A third requirement is permeability. This is so important to be ensured that blood flow can distribute and blood cells can distribute throughout the porous implant. So interadditive manufacturing, by building structures layer by layer from CAD or computer-aided design models, it's so possible by additive manufacturing to produce magnesium-based scaffolds with tailored porosity and strand sizes. It means effectively customizing the implant's modulus to fit each patient's anatomical needs. In other words, patient-specific design. This opens doors for treating bone tumors, fractures, or other bone defects, regular or irregular, more effectively. Traditional methods like die casting can't match AM's versatility in shaping these implants properly. Among AM techniques, laser powder bed fusion, or LPBF, sometimes referred to as selective laser melting, has been studied the most when it comes to fabricating magnesium implants. So this is our pivotal method for fabricating magnesium-based scaffolds. In a typical laser powder bed fusion process, we start by creating a digital bone model, often taken from something like a patient's MRI or CT scan. Then we put these files in a specific format, for example STL, in 3D modeling software. From there, software converts that model into thin 2D slices. Each of those slices guides where a laser should melt a thin layer of metal powder or not. In this case, magnesium metal. But these models in this stage referred mostly as files with G-code format. In other words, G-code file, which is sliced layer by layer, contains the commands for the 3D printer. It is also called a machine-readable file. In terms of 3D modeling software, we commonly use softwares like SolidWorks, but for laser-based 3D printing like SLM and in this field, laser powder bed fusion. Popular software in these fields includes Materialize, Magix, and NetFab, 3D Expert, etc. So let's go ahead. And as you can see in the figure 4, imagine a build platform inside a chamber where a very even layer of magnesium powder is spread out. A laser beam travels over the surface, melting only the sections that match the bone slice for that particular layer. Once that layer cools and hardens, the platform lowers slightly and a new layer of powder is rolled out on top. Then the laser melts the next layer, and the process repeats until the entire structure, shaped just like the computer designed, has been built up from the bottom to the top. Looking at the figure, you'll notice three main parts. Model design represents taking a 3D bone image and preparing it for printing. Laser additive manufacturing, so this is the process of melting the powder layer by layer using a laser system that follows the digital data model. And finally, bone implants. Here you can see the results. A porous magnesium structure that can help with bone regeneration by allowing cells and blood vessels to grow inside. So this method can create implants that match a patient's anatomy and offer many of the benefits of magnesium, like being lightweight. During laser-based PBF of magnesium, a concentrated heat source melts the powder briefly, followed by rapid solidification. Compared to conventional methods, this quick melt and solidify cycle refines the grain structure. However, at high temperatures, some elements in the Mg powder, magnesium powder, may vaporize, creating a buildup and increase of vapor pressure in the melt pool. The pressure can spatter and scatter molten material outward, forming areas of lower density that may help reduce the stress shielding effect in our bone implants. On the other hand, vaporization can also change the chemical composition of the material, which underscores the importance of using alloying elements that dissolve well and form corrosion-resistant phases. Ultimately, parameters such as laser power and scanning speed play an important role in controlling melt pool behavior, powder vaporization, and also the overall quality of the final part. There's a lot of quantitative information in this part of article, but let's say in this way, there's a sweet spot when you're using laser-based printing for magnesium alloys. Turn up the laser energy too high and you risk vaporization key alloying elements. And when you go too low, you won't melt everything properly, leaving behind unfused powder and lower overall density. Researchers tested various Mg alloys like ZK60 and WE43 under different laser powers and scanning speeds. In some cases, they nearly reached a full dense structure. In others, excessive vaporization or incomplete melting got in the way. Figure 5 visually captures how a scanning speed and laser power can shift the density or grain size of the final product. In short, the main takeaway here is that small changes in processing parameters can make a big difference in final quality of magnesium implants. Striking just the right balance leads to more complete fusion, fewer pores, and fewer issues with the elements vaporizing. That balance, in turn, has a major impact on the mechanical performance and corrosion behavior of the finished part. Key considerations for bone implants applications. Figure 5 highlights how adjusting laser parameters influences the density and grain structures of magnesium alloys. On the left A, you can see that scanning speed can significantly affect the relative density of ZK60. Too fast and you risk lower density, of course, as shown in the micrographs. On the right B, different laser power and scan speeds can lead to varying grain sizes in the Mg. In Mg 9% Al powder specifically. Each color-coded region suggests an operational window. Too low or too high and you might end up with brittle parts, poor mechanical strength, or excessive material evaporations, of course. But porosity can become a big challenge when using LPBF with magnesium. Even minor changes to factors like laser power, scanning speed, or layer thickness can change pore formation. And of course, the overall porosity distribution actually. And no single parameter works in isolation. As Table 2 suggests, each alloy composition also has an ideal processing window when it's most likely to form dense parts with minimal porosity. Another issue is hot tearing, which occurs when columnar grains become vulnerable to cracks under high temperature gradients. Because magnesium's behavior in LPBF isn't yet fully understood, researchers are still exploring the best alloying choices and printing parameters to reduce both porosity and cracking. And let's a little talk about the table 2. This table showcases different magnesium alloys like pure Mg, WE43, GZ151K, and GZ112K. they all are being processed under various laser power settings, scanning speeds, and layer thicknesses. Each set of parameters leads to a specific energy density, which is turn influences the final relative density of the printed part. You'll notice some combinations result in densities above 99%, while others dip below 90%. So in essence, the table underscores how even small changes in processing conditions can drastically affect the quality of magnesium-based implants. Whether that mean higher densities, fewer pores, or better mechanical performances. Alright, in the next episode, we'll cover the rest of the article focusing on mechanical behavior of the implants. So till then, goodbye and thanks for listening.